How's the audio? But I think we're good. All right. So this is for y'all Cal 2 folks of mine. Today, and I'm gonna erase this. This is not y'all. This is a differential equations class that I'm teaching. But for y'all, what we want to look at today. So we looked at integration by parts. So far as technique, we essentially have integration by substitution and integration by parts. So what we want to look at today is not necessarily a new technique. So the focus today you'll see is not necessarily a new technique. So we're not going to do some other grand pattern that we could use to do a lot of integrals. But what we're gonna focus on is a type of function. So we're gonna look at trig integrals. So we're gonna look at trigonometric integrals. So we've done some integrals of cosine, sine, tangent. It's not that we haven't done them so far, but we want to look at some specific integrals that you see decently often with trig ratios. So that'll be the whole focus today. This might be a slightly long lecture just because I'm gonna cover both section 8.3 and 8.4 in this. So 8.3 says trig integrals and 8.3 says trig integrals with substitution. What do you call it? Is it with substitution? Hold on. What's the name of these sections? Yeah, or they just say trigonometric substitution. So I wanna do both in one lecture because again, I want the focus today. So the focus today is not gonna be on some new method of integration, but just doing a bunch of integrals with trig ratios that, like I said, come up decently often. So let's dive into it. And in doing that, we're going to see as a common thread. So again, our focus today, like I said, I know I keep repeating myself, but I guess just bear with me. But our focus today is not a new method for doing integrals, but rather is focusing on a lot of trig integrals that come up more often than we would like. So because we're focusing on integrals specifically involving trig ratios and trig functions, the thing that we're going to see today, honestly, that we haven't played with yet, or the thing that you're going to need today to really recall and remember is honestly a lot of your trig identities. So both trig identities and some work that you guys did in pre-calculus. So the in pre-calculus, that portion of the course where you went over trig identities, what you'll see today is that those in particular are crazy useful for what we're about to go through. Yeah, pretty much. So those trig identities, if you need to pull those up on the side, or if you just need to recall those in your mind, just kind of have those up because they're going to be hella useful today. So let's start. Let's start with something like this. So this is an 8.2, number 3. They want you to do the integral of cosine of x to the 5th power sine of x. Actually, give me a second. Do we want to start with this one? This is good, but this is not really anything. Well, let's start with this. So we'll start with this, not because we need something new for this, but I guess maybe to bridge into what we're doing today. Um, so something like this. We want to take an integral of cosine to the fifth x sine x. So we got two functions multiplied. So like we talked about in the last two lectures, two functions multiplied. First, you want to see if you can possibly do a substitution. And then if substitution doesn't work for you, then you can we can try to navigate this using integration by parts. So, but the first thing is we want to see if we can use the substitution. But I also want to bring up this problem because it still doesn't look exactly like some of the integrals that we've seen so far. So again, we've done some integrals with trig ratios, but they were pretty simple ones. In fact, I don't think any of them or very few of them had two trig ratios kind of multiplied back to back. You're going to see that a lot today. So two trig ratios multiplied back to back with varying powers. And I would say in general, that is one thing. So it's not going to be every single problem, but that is one thing that distinguishes these trig integral problems from something that you've seen before this is trig ratios multiplied back to back with powers. You're gonna see that a good bit. So as we go through these problems, that'll be one of our goals is basically how do we handle trig ratios multiplied back to back with powers. Um, Now looking at this, so like I said, it is two ratios multiplied. So we haven't seen a cosine and a sine back to back so far, but it is two functions multiplied. We want to see if substitution works. So that is kind of my first question to you guys. Could we use substitution here? This sort of one function plugged into another with derivative outside. Give you guys a second to think through that. Notice that it kind of does look like that. So we have, it looks like cosine plugged into really a power function. Something to the, x to the fifth power. And we have this sine outside, and we do know in our head that the derivative of cosine is negative sine. So this does look like this is actually just simple substitution. And it is. So you say that u is cosine x, then really quick, we won't have to pause for it. Just take a second. If u is cosine x, what is du? Du is negative sine x dx. So then we can rewrite this integral as what? So I want to give you a second. Again, I won't even pause. I'll just pace. I want to give you guys a second to rewrite that integral then with that substitution. All right. So what you should end up with here. So this is going to be negative. Basically account for the negative we don't have here. But notice that we basically do have the derivative there, the du. Negative u to the fifth du. And then we can go ahead and work our integral out from there. So our integral, so actually, well, again, let me give you guys a second to do that. Again, I'll just kind of pace instead of us pausing, but go ahead and work out the integral from there. And then replace the u and all that good stuff. let's see what you guys are getting. So integrating this is gonna be -1/6. And it's u to the 6th power, but I'll just go ahead and write what it really is. So that'd be cosine x to the 6th power, all this plus c. And that is my indefinite integral there. So that would be my integral there. So we start out with something that, again, two trig ratios multiplied, but really is just substitution. So looks different than what we've seen, but no difference in how we solve it. Of course, that's exercise 3, right? So this is just setting the table for kind of where we want to go with this. Let's look at, I think I want to do 5 next. Then look at this again. So let's do 5 next. So 5, so then on 5, something like 5, we want to do the integral of cosine cubed x to the 4th x, yes. Now again, I have a cosine and sine back to back multiplied. This time they both have powers. So my first question to you guys is, I mean, it still bears a lot of resemblance to the previous one, so could we use substitution? I want you to take a second here. I will. I'll have you guys pause on your side and I'll pause on my side. See if you can make substitution play out or work on this. All right. So trying to do this with substitution. Hopefully you saw, so you run into some key, say some key barriers. So maybe my substitution is like we did on 3, u is cosine x. Problem there is my du is negative sine x, and I don't just have sine x here, I have sine to the 4th. And then maybe vice versa. So maybe you saw that and said, well, maybe my substitution is u is sine x. But then my derivative is cosine x, and I don't just have cosine x, I have cosine cubed. So the key, I call it a hurdle that you're running into is that both your cosine and sine have some power more than 1, basically. So if that's true, it's not going to be as easy as 3, because again, no matter what substitution you use, your derivative is just one of that trig ratio, sine, cosine, whatever. So what do we do with something like this? How do we kind of play with that? What we're going to do with this, we do at least want to take the hint of, so we want to use substitution, and it doesn't mean that we can use substitution, but we want to use substitution. Substitution always, so going back to 3, substitution essentially is always going to look like, again, 1 trig ratio to a power over here. Then, well, okay, if we're talking about just sine and cosine, so we'll talk about secant, tangent, all that kind of stuff on different problems. But if we're talking about cosine and sine, it's going to look like cosine or sine raised to a power over here, and just one of the other trig ratio there. So if I feel like I want to use substitution with this, or at least I want to see if I can code it as substitution, what that tells me is at the least I need to have sort of one cosine or sine kind of factored off or siphoned off here. So what I'm going to do with this is notice that basically, yeah, I don't want to give you guys just a rule of thumb here, but notice that on the cosine cubed, if I factor off a cosine factor, I'm just kind of splitting this into its pieces. But if I factor off cosine, it leaves me with cosine squared. So here's kind of the fun on this. I'm gonna factor off a cosine. Because again, what I'm trying to say is this is kind of what I want. I want an extra cosine just sitting out there. so that when I use the substitution u equals sine, my du is cosine x dx, and I have my du there. So if I factor off the cosine here, in my mind, what I'm trying to do again, so this is just critical thinking, kind of thinking your way through a problem with the concepts and tools that you know. If I factor off this cosine, then what I'm committing to is basically u is sine. The problem that I'm still left with though is this cosine squared. So in the middle, so I could say u is sine x. That would transform this part into a nice clean power function, and I would have du over here, but I'd still have this cosine squared. So so again, my instinct is I sort of want this problem to work out like the last problem. Now, like you guys saw, it doesn't immediately work out that way, but I'd like it to work out that way, where it's one trig ratio, or either cosine or sine, but one trig ratio to a power, with the other one just off by itself. And the huge hurdle right now is this big fat cosine squared just kind of sitting in the middle. So this is where, so I was telling you guys that what's going to become not only useful but incredibly necessary is all of those trig identities that you guys learned in pre-cal. So I want to see if this triggers something for you. So right now the cosine squared is a problem. By the way, just as a note, substitution didn't work. Maybe thought is then let's go to integration by parts. So integration by parts is going to be one of those, you're going to end up doing integration by parts a ton of times. In fact, let me think through this. Actually, integration by parts, this actually wouldn't even work on this. So the reason is you still would have to use substitution for like your u, especially your u, to get du. Well, u would work because it's just chain rule. But for your dv, you would have to use substitution, and there wouldn't be a substitution to use. So, I don't want to sort of go through all that because it'll take a ton of time. But integration by parts, unfortunately, it doesn't work on this either. But again, my instinct is I would like it to work like number 3. And so this is good. I want an extra piece like this. This is good. The derivative of sine is cosine. So if my u is sine, that works. Problem is this cosine squared in the middle. So then my next instinct is, can I turn cosine squared into a sine somehow? That's a really good question. Also kind of a really weird question, so like cosine is cosine and sine is sine. Can we really change the one into the other? So again, hopefully you remember some of your trig identities that you both used in pre-cal and in cal 1, because those are going to be the key and essential thing here. So the question is, can I turn cosine squared into sine somehow? And the answer is actually yes. So what trig identity allows us to do that? So remember, we have the Pythagorean identity. Pythagorean identity, one version of it says that sine squared plus cosine squared equals what? Equals 1. If sine squared plus cosine squared equals 1, then what does cosine squared equal? Good. So that means that cosine squared would equal 1 minus sine squared. Now, again, that's not part of your problem. They're not going to, they're not going to cleverly or, secretly put that over to the side for you to see. This is something you got to realize you need and bring into the problem. But this is hella useful because, like I said, the problem that we have right here is basically we just have this other trig ratio cosine there. And if we could somehow turn that into sine, I can maybe work this through a substitution. So we're gonna do this. We're gonna do this substitution. We're gonna replace cosine squared with 1 minus sine squared. This is sine to the 4th. 1 minus sine squared. And notice what that does. So immediately though, I mean, it's still just have the sine of the fourth over here. You still just have this other piece here. But now I can distribute. Before I can't multiply a sine and a cosine, let alone things to different powers. But now I can distribute. So I can multiply sine to the fourth there, sine to the fourth there. I end up with the integral of sine to the fourth x minus sine to the sixth x cosine x dx. And now I have basically two separate integrals to run. So now I can run this as two separate integrals. So I can run this as integral of sine to the fourth x cosine x dx minus the integral sine to the sixth x cosine x dx. Notice that each of these looks suspiciously a lot like this last problem. Just the roles are switched. So this on each of these then would guess, and your guess would be right, that the u would be sine x, my du would be cosine x dx, and now I can run each of these as substitution. So that's how we're going to start to handle problems like this. So if you got cosine and sine with different powers, but basically more than first power, then you want to use you end up using your Pythagorean identity to take part of one of them and turn it into the other, enough so that we make substitution work. So you factor off either. One way to think about this is basically whichever one has an odd power is naturally the one that you can factor off a cosine or a sine, whichever it is, but an extra piece. So you factor that off. Then you should be able to change the other one. So you should be able to change the other one, what's left over from that odd powered trig ratio to the other trig ratio, which should set you up perfectly to do substitution once you the algebra out there. So, anyways, so we can do substitution with these just like we did on number 3. So let me have you guys do that. So I'll pause on your side, I'll pause on my side. See if you can work both of these integrals all the way through from there. All right, let's see what you guys are getting then. So what I will do here, so basically the substitution for both of these is gonna be the same. So I'm just gonna write that up on the side here, that u is gonna be sine x. We talked about du, then cosine x dx. So this is gonna become the integral of u to the fourth du. This becomes the integral u to the sixth du. Then we can work these through. So kind of fast forward then. The integral here is going to end up being up to the 5th power and divide by 5. So it is going to be 1/5 sine x to the 5th power. And the integral there, let's see, I did. You're going to go up to the 7th power and divide by 7. So it's going to be minus 1/7 sine to the 7th power and plus c. And you have your integral. Easy enough. So that's really the key, or the key thing to learn out of that is, like I said, the lead is you want to take whichever one is odd, factor off that extra piece, then use Pythagorean identity from there to kind of work it into a place where you can use substitution. So much so that that even works for a couple more of this variety. Let's look at 9. There, they want the integral of sine cubed 2 theta. Then they have the square root of cosine of 2 theta d theta. Good. And so even though you see a square root here, so now we don't even have so we have sine raised to a third power. We have this 2 theta, which we'll see maybe in some later problems comes into effect. So you might need to think about double angle identities. But here we end up we don't have to. So you do have sine to a third power, but cosine isn't even raised to a, what do you call it, an integer power. However, still, because this is raised to an odd power, my first instinct here is I'm gonna siphon off this extra sine. So it'll be sine of 2 theta times sine squared 2 theta. And while I'm at it, I'm gonna go ahead and rewrite this as a power. So that's cosine really to the 1/2 2 theta theta theta. And notice that even with this, so even seeing an odd power like this, if u is cosine of 2 theta, my derivative is negative sine 2 theta d theta, and that takes care of those two other pieces. Like 5, what it doesn't take care of is the sine squared, but sine squared I can rewrite using Pythagorean identity. So I want to give you guys a second to rewrite the sine squared according to the Pythagorean identity, or use Pythagorean identity to rewrite it, and then distribute everything through. And then it's kind of, if you want to keep going from there, stop there, but just rewrite this using Pythagorean identity and then distribute everything through, and let's look at what the integral looks like after that. So go ahead and I'll pause on my side, you pause on yours. So this sine squared then should basically be, even just looking at this equation, you just move the cosine squared over the other side. So the sine squared of sine 2 theta, it's replaced with 1 minus cosine squared 2 theta. All still times cosine to the 1/2 power. So now we can multiply the cosine of the 1/2 through there, and I'm gonna move the sine 2 theta over with the d theta because I don't want it there anyways. It goes with that anyways. So we're gonna end up with multiplying through the cosine 1/2 through, so cosine of 1/2 2 theta minus, and then we're gonna add, so 2 and a squared 2.5 is gonna be 5/2, so cosine the 5/2 power 2 theta. All with the sine 2 theta, sorry. Sine 2 theta, d theta. Now, again, you notice we're gonna be able to do substitution here. In fact, this time, if you want to, you can just, don't even have to separate it into separate pieces. So we can just make our substitution from here. Our substitution is u is gonna be cosine of 2 theta. And if u is cosine of 2 theta, what is my du? My du is negative, actually, not just negative, but so it's gonna be negative sine, but in doing my derivative here, we do have a little bit of chain rule. So instead of just theta inside, we have 2 theta, and what's the derivative of 2 theta? That's 2. So my derivative here is gonna be negative 2 sine 2 theta theta. So notice that I have my du minus the -2. So like we were seeing on you're seeing on the lecture about substitution, I'm gonna have to adjust for that with basically a -1/2. So then this becomes the integral of u to the 1/2 minus u to the 5/2. Well, I really needed to. Doesn't really matter where we put this, but I guess times -1/2 du. And from there, you can do the integral easy peasy. I'll actually have you guys do that. This is quick, but nonetheless, pause on your side, I'll pause on my side. Let's work that integral. Sweet. So u to the 1/2, the power goes up to 3/2. Then this is not, the power goes up to 1/2 to 3/2, and then we divide by 3/2. We're gonna end up there with, so we're gonna have -1/2 times, sorry, 2/3, and u was cosine of, right, cosine of 2 theta, cosine of 2 theta, or cosine to the 3/2 power, 2 theta. And then the 5/2, that power goes up to 7/2, and then we divide by 7/2. So that's gonna be minus 1/2 times second. Yeah, so we're doing a minus times a minus there, so that just becomes a plus. Save all the theatrics there. So 1/2 times now 2/7. This is gonna be cosine to the 7/2, 2 theta. All this plus. And then we just work our multiplication here. So let me rearrange it, cosine, and you don't have to do that. Absolutely has no effect mathematically, but it's just pretty nice to see the positive first or the negative. It's also a good rule for life. Don't let negative things kind of color your perception, right? So if you see the positive things first, you can handle the negative better. Whereas if you see the negative things first, you're always going to see the positive as a little worse than they really are. Um, Cosine of 7/2, 2 theta. Sorry, I didn't put the fraction there, so it's gonna be 1/7 cosine of 7/2, 2 theta, minus 1/3 cosine of 3 to the 3/2, 2 theta, plus c. That is our integral of sine cubed 2 theta, square root of cosine 2 theta. Honestly, in general, as long as you can, for sine and cosine, as long as you can factor off, you got one with an odd power that you can factor off one piece, then you should be able to use your trig identities to remake it into a substitution problem. All right. But that last comment, or what you guys have seen with the last two problems, kind of begs the question, what if I can't? So what if I'm given some problem where I can't factor off one of the pieces? I don't have an odd power. So let's look at a couple of those. let's look at 11. Let's kind of get there. I'll go back. 11 wants the integral of cosine squared 3x dx. Let me make sure I got that right. So notice not only, well, notice a couple differences. I don't have a cosine and a sine, and the cosine that I do have is just is an even power. A second to, I feel like we actually should see. So there's a missing type of problem in their exercise set. I feel like we should see that first. Oh. All right, but let's look at this nonetheless. So don't have the other piece to work with. But also, again, notice that it's just an even power. So even if we wanted to factor off one piece and sort of do something there, that wouldn't work here because we don't have an odd power. So what do we do? I think a good first thought is we have been working with Pythagorean identity, right? So couldn't we just rewrite this using Pythagorean identity? And let's take that direction for a second. So if you were going to rewrite this using Pythagorean identity, how would that be written? Good. You could rewrite this as 1 minus sine squared 3x dx. Now the question is, does that make this something that we can take an integral of? Yeah, we could take the integral of 1 dx, so that's easy enough. But what about this sine squared? And hopefully you see that there kind of lies the problem. We basically traded a cosine squared for a sine squared, but we haven't traded it to anything that we can integrate. It's not that this was a good idea, because we at least got one part we could integrate, but we can't integrate this part. So what that means is just our Pythagorean identity, which we've used a lot in the previous problems, just doesn't help us here. It's helpful, just not here. So is there another trig identity that could help me? That's really kind of the key question here. So go back, look at your other trig identities. Is there another trig identity that involves cosine squared? Wait a second, there might actually be two of them that are useful here. Yeah, there's at least one that's useful here. And so going back to some of your other identities, one of the other identities that becomes that's helpful here, the one that's helpful here but becomes helpful a couple places, are these half angle identities. Half angle identity, the way it's actually usually written on the equation sheets is what's going to be helpful here. Make sure, usually the way this is written, one of my half angle identities is cosine squared of x is equal to 1 plus or 1 minus. I believe the way this works is cosine squared is 1 plus cosine of double that angle divided by 2. And there's a similar one that sine squared x, then I believe is 1 minus cosine it. So the surprising thing with sine squared is it's still cosine. It's 1 minus cosine of double that angle divided by 2. Let me verify this, but I'm pretty darn sure that's correct. So these, I think they're also are related to, or they're kind of used for what's called the power reducing identities. Nonetheless, so you can look at a sine squared and basically replace it with 1 minus cosine of double that angle divided by 2. And we can look at a cosine squared and replace it with 1 plus cosine of double that angle divided by 2. So again, another identity that's going to become very useful. So it's something you want to make sure you have memorized, or at least a good picture of it in your head. So I'm going to start this then by rewriting this using my half angle identity. So cosine squared of 3x then. So 3x then is sort of my x here. 3x is my angle. On the right side, it's going to be double that angle. So I should replace that. So if 3x is here, then I'm replacing over here, I'm getting double that, which is 6x. So I should replace this 1 plus cosine of 6x over 2. And notice if you do that, now we have no powers, and this is just a cosine function. But now we've reduced something that was a squared that we've been using a bunch of substitution for to simple, actually it's really a two-part function, but a simple two-part function, just a cosine, which is not even substitution, that's just an easy integral work. So that's one of the benefits of these little half angle identities or power reducing identities. Literally notice why they call it power reducing identity, because you're taking squared, reducing it to a first power, right? You're doubling the angle by reducing the power. Called half angle identity because this angle is half of the resulting angle. Anyways. So we've reduced it to something like this. That in this case, immediately we can just work that. So I'll have you guys work that really quick. So pause on your side, I'll pause on my side. Go ahead and work the rest of that integral. All right, let's see what you're getting. You guys got easy enough. Yeah, you don't have to write out all these steps, but I am going to break this into basically two pieces. So it's a 1/2 plus basically a 1/2 cosine 6x. I'm going to integrate each of these. So the 1/2, basically you add an x onto that and you're good. So this integrates up to 1/2 x. And then this one, so integrating cosine, that's going to integrate back up the sine. That's going to integrate back up the sine, but you also then got to divide by 6. So you're going to end up with 1/12. Not cosine, sine of 6x. All this plus c, and you are golden. That would be the integral. So the integral of cosine squared 3x is 1/2 x plus 1/12 sine of 6x plus c. I think for the sake of both time and sort of moving on to some of our other trig problems. Yeah, so you're gonna see some problems maybe with both the cosine squared and the sine squared in it, or with cosine to some larger but even power. So cosine to the fourth, cosine to the sixth. For those problems, you essentially just break it apart into its pieces, like so even powers. Um, you just keep breaking down each of them using these half angle identities till you get a form that you can integrate. Now, if you have more pieces there, just higher powers, you won't always be able to break it down to something like this where it just integrates naturally. You don't need any method, but you'll at least be able to break it down into a method or an integral that you can use substitution on. So you'll have some odd power there eventually of these, it's kind of larger and larger angles that you can then use a substitution on. Just, I do want to look at one of those examples, but also want to get too lost and do too many problems. All right. So actually, I was looking at some of the problems they have in the book, and what I've decided is I'm gonna sort of go forward with my own problems because they sort of don't have all the combinations. Not only that I think you should, that I want you to see, but that you should actually see, that I think you should actually see, just to get some mathematical technique under your belt. So I'll kind of rest of these, I'll just make up my own problems. So we were talking about this one where it was a cosine squared 3x dx. Let me erase this. Hmm. All right. Let's say, we wanted to do something like the following. So let's do maybe the integral of let's do the integral of maybe let's do sine, whatever, it doesn't have to be 3x. Let's do sine 2x, but let's do this to the fourth power. dx. So again, we're in a situation where we don't have the other trig ratio, which we would need for substitution. We need at least need one of them there. So again, that's kind of the point, hopefully, that you see over the stretch of these problems. We at least need one of the other ratio there. In this case, one either sine or cosine. But what we can do is, if you think about it, this is just sine squared 2x times a sine squared 2x. Or you can think of it as sine squared 2x squared. But either way, what that means is then, like the last one, I can replace sine squared with, in this case, 1 minus cosine, double the angle over 2. And then we can see, so what then we want to check, 1, can we take the integral from there? And 2, if not, what's the next step? Where do we need to go from there? So each of these is actually just 1 minus, so you'd replace this one with 1 minus cosine of double that angle, so it's gonna be cosine of 4x. One minus cosine 4x over 2 also here. Now, unlike the last one, I don't just have one of these where I can just simply take the integral. I have 2 of them, so I'm gonna have to do some distribution here and kind of see what I have left. So to kind of flash forward on this, so if you distribute this, you're gonna end up with 1 minus 2 cosine of 4x and plus cosine squared 4x all over 2 x. So the question to you guys then, so looking at that, can you integrate that? Integrate all of that? What do you guys think? But definitely notice, like the last one, we could, so again, we could split this up into separate pieces. We can integrate the 1/2, and we can integrate the -2 cosine 4x over 2, or just negative cosine 4x. But once we get to the cosine squared, we're gonna run into a problem there, because again, overall, the issue with this this integral to begin with is you don't have the other piece, in this case, a cosine that you would need for substitution. So there's no way we're gonna be able to do the substitution we would need to do for this. But notice that that piece looks suspiciously like this last one. So we then can go in again and replace cosine squared 4x with what it's equivalent to using the half angle identity. Then maybe like the last one, we can integrate everything from there. So let me just start splitting up the pieces here. So this is gonna be 1/2. 2 over 2 is 1, so minus cosine of 4x. And then on this last piece, what I'm gonna have is cosine squared 4x. I'm now gonna replace that with what the half angle identity gives you. So it's gonna be 1 plus cosine double that angle, double the 4x, which what is double 4x gonna be? Now that's gonna be 8x. So it's gonna be plus 1/2. Now it's 1 plus cosine of 8x over 2. Yeah, 1 plus cosine of double that 4x, which is 8x. All this dx. And we can multiply through, we'll end up with a 4 on the bottom. But now notice this is something we can take the integral of. We can take the integral of 1/2, we can take the integral of cosine of 4x. But once you multiply that through, you can take the integral of that. Let me multiply that through. That's then gonna be, I'll multiply through and then separate the pieces. So multiply through, you get 4 on the bottom, so we're gonna end up with plus 1/4. That we then can combine that. Sorry, so let me. But 1/4 Then we're gonna end up with plus 1/4 cosine of 8x. All of that dx. Then one more again, let me combine the quarter and the half there. So what we end up with overall, the integral 3/4 minus cosine of 4x plus 1/4. Something, no, I didn't. Second. That was already. 1/4 cosine 8x, all dx. Now this is something we can take the integral of. So looking back at these two problems, when you just have a cosine or sine raised to an even power, you're gonna have to keep, so algebraically, you're gonna have to keep substituting using the half angle identity, but at some point you're gonna get down to this place where this, again, this is barely substitution. So you don't even really need substitution. You should just be able to integrate everything as is. So let me give you guys a chance to finish that out then. Go ahead and integrate this from here. All right. So integrating from here, what you should have got is 3/4 x. Negative cosine, when you integrate that up, gives you negative sine. And then we're also dividing by 4, so minus 1/4 sine of 4x. And then cosine, when you integrate that up, it's a sine. Dividing by 8, so it's going to end up being plus 1/32 sine 8x, all plus c. That would be your integral. So the integral of sine to the 4th power 2x, 3/4 x minus quarter sine 4x plus 1/32 sine 8x. Then if I gave you a problem where maybe we had both of these even, right? So maybe, yeah, I don't know. I want to make this, see, but maybe sine squared x, cosine squared x dx. Then what I still can do is replace each of these with their half angle identity. And notice when you're working with the half angle identity, everything gets converted to cosines. So this problem is actually going to work out a lot like this last problem, where once I convert this, so if I sine squared x is going to be 1 minus cosine 2x over 2. Cosine squared x is 1 plus cosine 2x over 2. When you multiply this through, you're going to end up with a squared term. Then you can use the half angle identity to replace again. So basically algebraically, you again are going to work yourself down to some situation like this, where you'll see different powers here on your cosines, but they're all going to be cosines, and you can integrate those all from there. For the sake of time, I don't want to finish that out, but I think you guys kind of see the pattern from here. All right. So every problem so far has been with sines and cosines. So basically powers of sines and cosines. The next thing we want to look at, and this is still out of section 8.2, is we want to look at powers of secant and tangent. And everything that we do for secant and tangent, by the way, if you think back to the derivatives and the integrals that you know, should work the same for cosecant and cotangent. So we're just gonna do it with secant and tangent. All right, so let's do similar types of problems, but we're gonna use the two ratios secant and tangent, the trig ratio secant and tangent, but raised to different powers. So again, what I'm gonna do is I'm gonna start with sort of a base example that gives you some base technique, then build it up by changing the powers and seeing what's different as we go from there. I want to start with maybe something like this. Let's do the integral of maybe tangent cubed x secant squared x. Dx. I want you to think about tangent, secant, etc. Think about those derivatives and integrals you know. And I guess my question to you is that, just like the first problem we did with sine and cosine, could this be done with straight substitution? Especially because we just saw a lot of problems with sine and cosine where once the powers were above one, we couldn't do it with substitution, right? So we had to use trig identities to sort of replace things in some sense, like kind of cipher them down algebraically into a place where you could use substitution. Or like these last ones, you could just plainly integrate. So let's start at the same place. Could you use substitution on this? I'll give you guys a second to think about that. I'll just kind of pace back and forth. So what do you guys think? So it ends up on this one. So on sine and cosine, we needed kind of one extra sine or one extra cosine. This one does work straight by substitution because, so remember, what is the derivative of tangent? Derivative of tangent is secant squared. So kind of in a similar way we saw with sine and cosine, as long as you have a secant squared hanging out, or you can make it so you have a secant squared hanging out, then it should work by substitution. So like here, my u is going to be tangent x. My u is tangent x. What's my du? That's going to be secant squared dx. Secant squared x dx. Notice that's my du then. So this is the integral of u cubed du. And what's the integral of u cubed du? Just take a second and do that. Good. That's u to the fourth over 4. So the answer here is going to be tangent 1/4 tangent x to the 4th power all plus c. So when we're doing trig integrals with powers of secant and tangent, one of the strategies, one of the things we want to look for is the secant squared. Because then I can use tangent as my substitution. So then to continue this idea, so what if I had, so we need if we're gonna use u as tangent, then the nice thing is we need a secant squared. Then similar to what we saw with sine and cosine, let's say I had something like, I don't know, a tangent to the fourth, and now let's do a secant to the fourth. Um, X. But with sine and cosine, when we couldn't just do straight substitution, then we would look to kind of factor off a piece, then algebraically rearrange the rest of the function into something where the substitution would work. But we factored off like a cosine or a sine because we would need that for our substitution. So back to this. So the first question is, does substitution work on this? Or at least the same substitution we were trying to do here. And hopefully you see that it doesn't, because again, the power is higher than squared. So again, the first two problems that we saw with sine and cosine, the first one worked with substitution because the cosine or the sine was just first power. But once it was above a first power, we needed, substitution didn't work right away. So that's when we factored things off to try to make substitution work. So we're gonna see a similar thing here. If this is a squared, secant is a squared to begin with, gravy. This is just substitution and it's easy. But if it's not, then I'm gonna factor off a secant squared and see if I can still make substitution work. I'm gonna factor off secant squared here. So this is gonna become secant squared x. There's another secant squared x dx. And again, this is nice because if u is tangent, then there's my du. So right now, this is compared to how I started, this is in a much better position. I could call tangent my u, and that's my du. I have u to the fourth du. The only problem is this secant squared. So this, again, you saw the same thing with sine and cosine. The sine and cosine problems. When you factored off that extra cosine or that extra sine, everything was good except for the middle because you were left with this extra piece that was sort of the other trig ratio, right? So how did we solve that issue? Good. We used Pythagorean identity to change. So like if we had a sine squared, we changed it to 1 minus cosine squared. Or if we had a cosine squared, we changed it to 1 minus sine squared. We basically just changed it to the other trig ratio and worked out our algebra from there. So a good question. Again, as a problem solver, you want to reuse old techniques as much as you can if they work. So a good question is, could I play the same game here? Could I somehow turn the secant squared into a tangent? And hopefully you remember from pre-cal, yes, you can. So those same Pythagorean identities, the Pythagorean identity that we used in cosine and sine, there's a Pythagorean identity linking tangent and secant together. Tangent squared and secant squared, as well as cosecant squared and cotangent squared. And leave the way this goes and make sure I get this right. So again, looking at our Pythagorean identities. Actually, let me write the first Pythagorean identity we're using, and from that I can quickly figure out the other two. First one is cosine squared theta plus sine squared theta equals 1. So the second one should say 1 plus 1 plus tangent squared theta equals secant squared theta. There's even a third that would say 1 plus cotangent squared theta equals cosecant squared theta. These are the three Pythagorean identities. I think I mentioned this. It was either in the last lecture. I'm also teaching a Cal 1 class right now, so I may have done it in one of their lectures. But I think I mentioned in the last lecture that again, there's a connection. So these Pythagorean identities, not only do they just tell me sort of equations that work, they give me an interesting connection. So it tells you that cosine and sine are sort of linked. But it also tells you then that tangent and secant are sort of linked together, and so are cotangent and cosecant. And I'll just kind of leave that there. So there is a interesting kind of conceptual link or pairing between those particular trig ratios due to Pythagoras, basically, due to right triangles. Anyway, so back to this though. So again, if I want to choose u to be tangent, what this is suggesting is u should be tangent because then this is my du, but I have this extra secant squared there. Now let's just go and replace secant squared with 1 plus tangent squared. So we're gonna have tangent to the fourth x times 1 plus tan squared x with still my secant squared x dx. But notice what this does, just like with the sine and cosine the sine and cosine problems that we looked at. This converts everything basically to the left of your du to tangent. That's what you want because you want to replace you want to do a substitution of u is equal to tangent so that this is my du. This not only just conceptually, but practically kind of achieved our goal. This now so I'm going to do the same thing we did with sine and cosine. I'm going to distribute, but after that, this is going to be something where I can substitute u for tangent, then integrate by substitution from there. It's really kind of the same play that we saw that previous problem with sine and cosine. So let me have you guys do that. Go ahead and start the distribution and work the rest of the integration out from here. So pause on your side and I'll pause on my side. All right. So distributing here, what you end up with is tangent to the fourth x plus tangent to the sixth x secant squared x dx. Then we can make our substitution here. So u is going to be tangent, du is going to be secant squared. This is the integral of u to the fourth. It's u to the sixth du. So my answer ends up being 1/5 tangent the fifth x plus 1/7 tangent the seventh x all plus c. Good. Good. So like I said, kind of the same play out as we had for the sine cosine. Now these have all worked. Well, seconds. Now let's look at maybe something like, say we had something like tangent to the third power of x. It's maybe secant. Let's do secant to the third power of x. X. I want to look at this because then again, so I think that maybe the first thought is let's try the same approach. Let's factor off a secant squared. Because we're kind of assuming u is going to be tangent, and so the derivative of that is secant squared. So what that leaves me with is secant x secant squared dx. And again, we get the part that's going to be du. We get the part where we're going to do our substitution, and again, we get something in the middle. But let's look at this thing in the middle. This thing in the middle is just secant x. And do we have a replacement? So that just like on the last problem, what we'd like to do is turn this into tangent. And we turn secant x into tangent. Good, and hopefully you see that we can't. We can turn secant squared like we did on the last problem into tangent because secant squared equals 1 plus tangent squared. But secant x, I don't have a trig identity that converts that to tangent x. It rewrites that in terms of tangent x. So overall, when secant is odd, we kind of have a problem. Because at least if I wanted to use the substitution of u being tangent x, because I'm going to end up with an odd piece in the middle here that I can't convert to tangent. That's the first thing to realize. Again, not a bad move. Not a bad move to factor off the secant squared. You just end up with a piece here that we can't convert to tangent. So we're kind of back to the drawing board then. Now maybe what's the next natural thought then? So if we can't factor off a secant squared and get this basically everything converted to tangent, so we can use the substitution of u equals tangent. What's maybe the next natural thought? So you as a problem solver, as you know, trying to work your way through this problem, then it's like, well, maybe let's reverse it around. Maybe my substitution is u equals secant, or I want to try figure out how to use u equals secant as my substitution. So if u is going to be, so really quick, if u is going to be secant x, what is my du? Be a second on that. Then my du is going to be, so the derivative of secant is secant tangent. That cool and odd type of derivative where the derivative of it is itself times another piece. So it sort of expands, it adds another piece onto it. So if I want to use secant as my substitution, or u equals secant, then naturally what I need to be able to factor off or siphon off of this, or what I need present to have my du, is not just a secant, not just a tangent, but both. So the siphoning off or the factoring off you're going to do here, again, it's the same idea. So it's the same play overall, but it's slightly different than using u as tangent, because there we're keeping a secant squared. And even when we did sine and cosine, you would leave one cosine or one sine out to the side, right? So that to match your du. But now you're going to need to leave not just a secant, but both a secant and a tangent. But this still gives us a way forward. So, and a lot of what we're doing here actually, honestly, is trial and error. So again, you saw that the u substitution for tangent wouldn't work. So then the next thought is, well, let me try it for secant. If I'm going to use secant, I know du is secant x tan x, so I need to factor off a secant and a tangent from this. If you factor off a secant and a tangent from this, what does that kind of leave you with? What's the other part? The other part is tangent squared, secant squared. So I'm going to literally just factor off a tangent and a secant from those. So tangent squared, secant squared times secant x tan x dx. Notice then that we're back to a situation where my substitution not only starts to work, we're back to that situation where it almost works, right? So if you secant x is my substitution, then this is gonna be u squared, this is gonna be du. However, again, I have this sort of obnoxious extra piece here. I have this tangent squared. But just like not only the previous problem, but again, how the several problems with the sine and cosine raised to powers, if I have this extra piece, then the next, the good strategy, the next thought as a problem solver is, well, if I could just turn this into secants, then we're good, right? Because then everything's a secant and it'll work for the substitution. And how do I turn this into secant? Back to using this Pythagorean identity. So using the Pythagorean identity, the tangent squared, how can I rewrite that? Things, with secant, what can I replace that with? So now just with this equation, you're going to move the 1 over here. So tangent squared is going to be secant squared minus 1. So I'm going to replace tangent squared with secant squared x, sorry. Secant squared x minus 1. That is still times secant squared x. We still have all the pieces over here that are going to make my du. And notice that now, like you saw in the last problem, like you saw in several problems now, quite a few problems, all you got to do is distribute and everything's going to be secants and the substitution's going to work. So again, on a lot of these problems, you'll see your overall goal is to make substitution work. And sometimes it works right away, but most of the time you're going to have to factor something off to sort of make that substitution work and then turn one function into another using Pythagorean identities, or maybe half angle identities. But that's what we're trying to get to. That's your overall kind of strategy in these problems. But just like the last problem, now you should be able to do this. You should be able to distribute that through and then work your substitution and get to an answer. So go ahead and pause on your side. I'll pause on my side and let's work that. All right, so let's see what you got. Let's just kind of work this through. So this is gonna be the integral of secant fourth power x minus secant squared x, all with secant x tan x dx all out to the right. So using our substitution here, easily see that this becomes the integral of what? U to the fourth minus u squared u. Integrating, what y'all should have got was 1/5 secant to the 5th x minus 1/3 secant to the 3rd x, all of this plus c. That would have been the integral there. Sweet. So again, a very similar solving, or what do you call it? Just play through as you solve for the sine and cosine. So but the other big thing about this particular problem is just seeing that the substitution u equals secant x works as long as you factor off a secant x tan x. So that should work for you. I will say then that, so if I was going to continue on with this, or just kind of continue the same track that we had that with sine and cosine, we'd have to have some problems. We'd try to see some problems where we could essentially use something like a half angle identity. But it ends up, could we turn these into? Second, I actually want to play with this in my mind really quick. So could we turn this into half angle identities for that? You could. Tangent. Well, so basically, we could go on with some problems where we essentially try to, so if I was to mimic what I did with sine and cosine, then the next thing we'd look at is problems where you just have tangent to a power or secant to a power. And the assumption is then those work using versions of the half angle identities that you'd have for tangent and secant. And I'm not saying that doesn't work, but it takes a lot of time, takes a lot of algebra. And so basically saying this is kind of fine for today. This will get us where we need to go, 8.2. Now that I think about it, so I wanted to make this lecture, well, let's see, I wanted to make this lecture both 8.2 and 8.3. I'm gonna pause it on my side. Give me a second to look through how much we really need to do in 8.3. Hold on. And actually, I'm really sorry, guys. The whole time I've been saying this is 8.2. This is section 8.3. So what I mean is actually 8.4. So I'm gonna look at 8.4 really quick, to see how much there really is to do in that section. All right, yeah. So there's actually not a ton to do in 8.4, but it's still probably gonna take me another hour and 15 minutes, hour and a half to, you know, total time on my side to get the lecture done. To get that part of the lecture done. So let's leave this here. So this was 8.3, this trig integrals, and we'll come back and do what's called trig substitution. As you know, just a finish off to really just a bunch of integrals either with trig ratios or using trig ratios and using trig identities as a way to move through your integrals. So as a way to kind of basically get the algebra going and get it to a place where you can integrate it. But okay, so we'll come back for trig substitution. That'll actually be a shorter lecture than usual. All right, see you guys then.